Okay. Like that music. I'm a little under the weather, but I'll try to get through this session with you, and hopefully I won't share the joy with you. Anyway, what we want to do today is we want to talk a little bit more about transformations, and this is kind of the starting point for understanding this material, and we'll continue to use these things throughout the course. So it will become automatic for you with a little practice. And then we want to start doing some real stuff. We want to start modeling using our algebra skills, the things we've been learning in the last few weeks to actually tackle some real type of problems, and we'll just take some problems out of the textbook to do that. All right? So let's go ahead and let's do a couple examples with transformations to sort of see the pattern that exists no matter what f of x you pick. So remember, what we're starting with is some function, and we could call this the old or the elementary function, and we then want to take something or make it more complex. So why don't I start out with something more complicated than just a simple function from our library, and then let's see if we can see what these transformations are that exist in that. So here is a new function. Let's say, and you pick one. Pick one of those out of our library. We had a variety of them we've summarized before.
Y equals x squared.
Okay, y equals x squared. So I'm gonna make it fancy. Let's say it's minus 4 times x plus 2 squared minus 10. Now, does everybody agree that this is an x squared kind of a function? Is that comfortable for people? Okay. While we're at it, let's apply the same transformations. Now, what are the transformations that you see that happen to x squared here? What are the items that you see here that cause the transformations? The negative 4 and the minus 10, right? Okay. Those numbers are the things that cause the basic x squared graph that you're familiar with to be transformed. Okay? Somebody else give me a different one of our library of functions. Cube root, okay. Y equals minus 4 cube root of x plus 2, and then off the tail end of that, subtract 10. Same basic type of idea, isn't it? Same transformations, except applied to the cube root function. Notice what's underneath the cube root, the x plus 2. Over here, what's inside the squaring function is x plus 2. And then on the outside of that, you observe these other numbers, minus 4 and minus 10. Okay, so look, they look pretty weird, pretty strange. Now, notice that the old function from your library is, the basic character of this thing is a y equals x squared. So this is your old function down here from your library, and up here is the new function that we're trying to understand. Similarly, over here, the old function is y equals cube root of x. Now, next to the old functions here, we could draw a little micro sketch. Here's your x squared function that you've got in your head. Over here is your cube root function that you may or may not have in your head. Although once I show it to you again, or you see it in the book, this is not x cubed. This is not the cubic, right? This is the cube root. And if you don't have it in your head, here it is, looks like this. All right, and this is one of them that's in our family. Everybody okay so far? Jennifer?
I thought it was more flatlined in the middle.
Well, you mean flatter?
Yeah.
But still having this character though, right?
Yeah.
Okay. Now, for instance, if I went out to 27, if I went clear out here to 27, how high up would that be? Cube root of 27 is
3.
3, right? What times itself 3 times gives you 27. This would only be up 3. So you can see I've sort of exaggerated the scaling there just so we can see the graph nicely. Okay?
But it would follow the y-axis a little bit more than that, right?
It would, excuse me?
Wouldn't it, it would follow the y-axis a little and get a little straighter there, wouldn't it?
It actually, if I had equal scaling, like if this was 27 here and that's 27 there, then this thing would look almost like a flat line and you'd hardly be able to see it. Right? Is that okay? All right. So anyway, you want to have these fundamental old functions in your head. You look at the complicated thing and you go, okay, the only thing that's inside here being squared up here on either of these problems inside the actual basic function is x plus 2. And over here, what's inside the cube root function is x plus 2. What's outside it is really an adjustment that's happening to the y value, these old y values here. Now watch this. Can't we do a little bit of algebra up here on this complicated thing? See, what's going to happen is we're going to have complicated looking equations like this, functions like these, and we want to be able to quickly sketch them. So with arithmetic, can't we bring this 10, can't we bring that subtracting 10 over to the other side? And it becomes y plus 10 equals that. And then over here, we can bring the 10 over similarly. Right? And notice that 10 is outside of the actual character of the function. So now, I brought it over here. Now we also could do something with this negative 4 to move it away from this quadratic expression. And we could move the negative 4 off of the cube root expression by doing what? Divide both sides by negative 4. Divide both sides by negative 4. If we do that, the thing is going to look like this. And similarly, on the cube root function over here, y plus 10 over negative 4 is equal to this cube root function. Is that all right? Isn't this y up in here, all the way through here? Isn't this y this new y? Right? Aren't these the new y values that are going to show up when we draw the picture? These are the new y's. And so look what's happening compared to the old y's down here. Isn't this old y being replaced with this new y plus 10 over negative 4? Do you agree? Aren't we taking this thing right here and replacing it, this thing, and replacing it with all of this? Does that make sense? All I did is arithmetic up here to get this thing to look like this. Okay. And all I'm doing, what am I doing to this old x?
Plus 2.
I'm replacing this old x with this new x plus 2, right? Now look at the math. Let's just do it. Take this thing on this y stuff right here, multiply both sides right here by -4, and so we have -4 times the old y is equal to the new y plus 10. And now go ahead and solve this for the new y. Now I'll just write the new y on the left because that's the way we usually like to write the thing we're looking for. The new y is then going to be equal to -4 times the old y. If I subtract 10 from both sides, doesn't it look like this? Right?
I don't understand why you're using old and new. That concept is just escaping me.
Okay. This is old stuff that we're real familiar with. This is something strange, right? Okay. And so I'm just calling this something new. We're familiar with this. We're familiar with y equals x squared and what it looks like. Its domain, its range, its critical key points like its vertex. So we're familiar with this thing. Really, we're very comfortable with this. We're trying to become comfortable with something like this. I'm just calling this new. So when we draw this picture, we're going to have a new x values associated with, and then associated with those new x values are new y values. So the picture is going to look different than that thing. Okay? And a bunch of you probably had the same question she just had. Why am I calling that the new and this the old? Is that okay with everybody? The math here so far is real simple, isn't it? You're just not sure why I'm doing what I'm doing, right? Now look at what this down here is telling us. If this old y is being replaced with this, and I solve for what this new y is, look at what it's telling us happens to the old y's. Don't we multiply the old y's times -4? So what's that going to do if I multiply these old y's times -4? It's going to take these old y readings, which are these y values here, the heights, and these are our old y values, and it's going to multiply them times -4. It's going to make them 4 times as big, isn't it?
But upside down.
And upside down. You with me, Todd?
Oh, yeah.
Okay. And so what we're going to get is if I do just that part of it, it would look like this. Tall and skinny, 4 times as much everywhere. But upside down, right? Negative. And then, what do I do here? Subtract 10. What's that do to all these y values here? If I take 10 off of these y values, what's that do to it? Help me. Down, doesn't it? Doesn't it take them down 10 more? And so what happens is these old y values being up here, these are the old y values, these heights here, it's going to be hard for me to fit it on here with my scaling, but it's going to be tall, skinny, upside down, and then down 10. So it's going to be sitting down here like this. So here, these are now the new y values here. At the same time we do that, what happens to the x's? What are going to happen to the x's?
You're going to move them to the right.
Okay, look at what, now let me see if I can tuck this in to get it on this board here, which is a fairly small board to work on. Isn't this new x going to be equal to the old x minus 2? So what am I doing to all these old x readings that you see right here?
Move them left.
I'm going to bring all these x's readings that you see, I'm going to bring them to the left too, including the ones over here. They're going to come to the left too. Question?
Is the point of this to simplify the y we were given?
The point is to have us have a quick sense of what this picture is going to look like.
Can we do that without doing all of that algebra?
Yes. After, once you understand what's happening here, and I'm showing you the details so that you don't just blindly believe me and say this turns it upside down and makes it 4 times as tall, and this causes it to jump 2 to the left and down 10.
That's what I thought we were
Yeah.
down.
Yeah, and if you got that skill, you're okay. You're fine. That's the way I do it. What I just said.
But other things can.
But I'm explaining why it works the way it works, and that may confuse some of you. Okay? Is that true? Okay. So I'm showing you why it does what it does. It's kind of the background, it's the detail as to why it does what it does. So what we've got, in a quick sense, let's see if this will show up on the screen, I think it will, is I'm going to take and distort my graph by realizing that I have to take the old y readings on my parabola, my simple parabola, I have to make them 4 times as great and negative. So that's going to make it tall and skinny and upside down, and then it's going to get drop 10 and then 2 to the left. So my picture then is going to come down over here, 2 to the left and down 10 and be tall and skinny pointing downward. That's a quick sketch of this function, of this thing up here. Hang on just a second with your question in the back. Let's do the same darn thing with this cube root over here. Aren't the transforms identical? So what's going to happen is this cube root graph is going to be 4 times as tall. So it's kind of getting vertically stretched, 4 times as tall. It's going to be turned upside down, and it's going to be kicked 10 down and 2 to the left. Quick sketch. 10 down, 2 to the left, and it looks like an upside down cube root that's been vertically stretched somewhat. And I'd label this point -2, -10. Getting it? How many of you are feeling like you're starting to get it? That's a good sign. The people I'm worried about are the ones who didn't raise their hand. Okay. Okay. Yes.
Wouldn't it be
Tyler?
to the left 2 cube root? Cube root 2?
It's just, here's why it goes to the left too, right here. You're taking these old x's inside that cube root and you're replacing that with x plus 2, some new x plus 2. So this new x reading plus 2 equals the old x. You're replacing this x with that. And if you look at what the old x is, if you look at what the new x is here, it's the old x readings -2. So you're taking all these old x readings here and you're kicking them 2 to the left. Yes, question in the back.
So why'd the graph flip upside down then?
Negative.
Oh, okay, times by 4 and then
Mm-hmm.
And then
Okay.
did it also narrow because of the 4? Made longer. So the curve is going to be more pronounced?
4 times as tall, 4 times as tall, right?
So the
'cause
curve will be more pronounced on
Yeah.
the new one.
Well, depends on what you mean by pronounced. It's 4 times vertically stretched, 4 times vertically stretched, and then turned upside down because of the negative. Okay, now, how can we check, how can we confirm that what this story I've been telling you is true? We have our,
Accept it and move on.
just accept it blindly on blind faith and move on, right? But let's grab our graphing calculator and see if it does that. And here you'll see why I want you to be able to do this in your head, is because then you're going to turn this on with your calculator and you're going to see something interesting here. So with the graphing calculator, we go up to our function set, and let's take and enter, which one do you want to do, the parabola or the cube root? The cube root one? So we use our negative key, -4, and then you go to the math key, math, item number 4. Inserts the automatic cube root function into your calculator. And then inside the cube root, we're going to put our x plus 2, and then we're going to subtract 10 from that. Okay, now when you're using your graphing calculator, what do you do after you enter the function? We just entered the function. What's the next step? We think of a viewing window. We think of a viewing window. We use our brain. So I hit the window key, and I've got an image in my head based on that algebra we did. So it looks to me, if you go back and look at your notes there, it looks to me like this graph's going to go off to the left pretty fast. Doesn't it? If you look at that picture of the cube root, it's going to go off to the left pretty fast. So I better set a window pretty far to the left. So why don't I say -30 as a first guess, and then I'm not going to go too far to the right. Why don't I say 10 to the right and put tick marks every 5? 30, -30's on our left. So we have a spread of 40 across our window. Now vertically, we're dealing with a cube root function, so we know cube roots don't rise or fall very quickly, but we are magnifying it by a multiple of 4, aren't we? So it's going to go up and down quicker than just a plain cube root would. So I'm going to go ahead and just take a rough guess. How about -20 to 20 and put tick marks every 5? So this is our first educated guess for a viewing window. Okay? Educated guess for a viewing window. So now I hit graph. I run out of batteries? Okay. Got a dead battery. So, okay, we got the sound back? Okay, good. So what I did, folks, just if you missed that on the DVD, we took an educated guess on the viewing window based on the paper sketching or sketching we did on the board, and then I hit the graph key once I had this window set. And I get a picture looking like this. Notice what's nice about this image you see. There's a lot of nice things about it. It's lovely, thank you. Okay, but what I mean by nice is, doesn't it show what's called the end behavior? It's showing that it's rising slowly as it moves off to the left. It's also showing other details. It looks like it's got a 0 here, doesn't it? Somewhere here, a 0. And then it looks like it comes down and it goes through a very important point down here, doesn't it?
Y-axis.
Well, hold it. What point right in here is really important to us?
Oh, a local max?
No, there's no local max there. Look, think about what we've been doing. Huh? There's a spot here. What is this spot based on what we talked about a few minutes ago? -2, -10, -2, -10, and then it continues to fall and then moves off to the right, dropping slowly. So it's got the end behavior. End behavior, falling slowly to the right. Oh, it's also got, as somebody mentioned a moment ago, a Y-intercept. Okay, now what I want to do is, actually I think we'll live with this window. That was not too bad of a guess. Okay, so watch this. If I now turn trace on, I can sort of check to see if my transform information was good. If I insert -2 in my trace key, it shows me right on -10. Okay, very nice. And I like the combination on the video there. It's got both the board and I can move my hands around in the air here too. Okay, so what you'll observe is you can see that very important point, -2, 10. That's that transformation. And every other point on that graph has been shifted 2 to the left and down 10. Now let's come back up to the board. Let's come back up to the board and take this function again and look at it. Watch this. If we come in here and insert a -2, we better get what? Help me. We better get -10 as an output, shouldn't we? So if you put -2 in here, look what happens. Cube root of 0 minus 10, and what do you get? -10. There's that important point. There's that important point. Okay? Let's try something else. Let's use algebra. Let's use algebra to locate the 0. The 0 that we saw in the sketch. So what do I do to find zeros on a function? We put y equal to 0, don't we? Y is our f of x value, so we make that equal to 0. Right? Everybody feeling good? Now this takes you back actually to intermediate algebra. And now how are you going to solve this thing? How are you going to solve this? You have to isolate this x, don't you? Now you've all had a year of algebra already. You should be helping me on this, okay? We're going to keep the 10, the -10 over to the other side, aren't we? We're going to divide by -4. In other words, we're going to isolate the cube root, aren't we? We're going to isolate the cube root. So the cube root of x plus 2, we get that isolated as our first step to solve this, is going to be 10 divided by -4, isn't it? When you move that -10 to the other side, it becomes +10, and you divide by -4 both sides to isolate the cube root. And then do we leave the 10 over -4 like that? No, we always reduce fractions if possible. So we reduce this fraction to the common factor, 2 times 5, and a -2 times a +2, and we lose the +2 factors, and we end up with -5 halves. So we have the cube root of x plus 2 is equal to -5 halves. This is called a cube root equation. How do you solve for x in here?
You have to take it out of the cube root.
How do you get rid of the cube root?
You cube both sides.
Don't we cube both sides of the equation to get rid of the cube root? So let's come up over here. So we're now going to cube the cube root. And we have to do this to both sides of the equation. Let me back you up to something more familiar from your basic algebra background. What if you had square root of x equals 7? What do you do to both sides to solve that? You square both sides, don't you? Aren't you undoing the square root by squaring both sides? Yeah, and you get x equals 49 out of that. Okay? We're doing the same kind of a thing here. We isolate the cube root, and then we undo the cube root process by cubing. The formal name in mathematics for that is called applying the inverse to both sides. Later in the course, we'll talk about that. So when we do this, we get x plus 2. We have released the thing we're looking for from that thing that was holding on to it. And over on the right side, we get negative cubed is still negative, isn't it? Negative. and you cube 5 and you get 125 over 8. And then move the 2 over to the other side. And now, I'm solving for the exact 0, aren't I? I'm solving for the exact value of the 0, where the x-intercept is. And so now we're back to arithmetic. We need a common denominator. So we know the common denominator clearly to add these two numbers together is an 8. So we have to apply, we need an 8 denominator here, so we have to apply to both the numerator and the denominator of 1, we have to apply a factor of 8. So what we're going to do then is we're going to take 16 away from minus 125, and what does that give us? 125 and a minus 16 is negative 141, isn't it? So we get negative 141 divided by the denominator 8. That is a what? What's it called? It's a fraction, that's good. Okay. It's a 0, isn't it? Isn't this the 0 of the function? So minus 141 over 8 comma 0 is a point on the graph. How do we check that, folks? We don't look in the back of the book because this problem didn't come out of the book, did it? Okay, so what we do is we turn our calculator on. Let's come back to the screen. Here's the picture. And so what we do, we're still in the trace mode. And now we're going to punch in negative 141 divided by 8. And we're hoping for what? When I hit enter.
0.
We're hoping for 0. And there it is, folks. The precise, you can see the precise y value being 0 there. Feel good? Okay. So what we've done is we've taken a transform problem, and I've explained to you the background of why the transforms do what they do using these two examples. We did a parabola, and then we did more detail here with this cube root function. And you can see how they behave. Okay. So let's leave the transform subject for the moment. And I also showed you how to use your calculator effectively. One final thing with your calculator is what you want to do on that. And I'm going to go ahead and erase part of this work. Is one thing you also want to include in your work is then a sketch including the viewing window, which I believe that we used a negative 30 because the scaling marks up there were 5s, I believe. I think we had minus 30 on the left, looks like 10 on the right, minus 20 and top, minus 20 and 20. And then the axes look something like this. And then the quick sketch where it goes off the screen, where it has its zeros, where interesting points might be, and where the Y-intercept is, and where it goes off the screen. And then you can quickly come in and sketch that thing roughly like this, and you can label a few of those important points. Like that. And the Y-intercept, did I ever do that? I don't think I ever did it. But you can look at the original function and put x equals 0 in, x equals 0 into it, and that would give you negative 4 times the cube root of 2, right, minus 10. And that value is not going to be exact. This is the exact reading. The approximate reading with your calculator, without having to jump to the, you don't have to jump to the screen there. You can just put a 0 in. It's minus 15.0397. 15.0397. There's your Y-intercept, folks. This point right here. Okay. So that gives you a pretty good summary of the concepts involved here at this level using transformations. Okay, let's change topics now. Let's talk about modeling, doing some real world type of stuff. In our book, I believe we're here in section 2.6 on building math models, and let's look in the textbook, and you can go to, with your Math Excel, you can go to the study plan, and you can go to this section in the book and find problems in the database on the computer system that match many of the problems that you see here. And so why don't we take, is number 7 in your homework? Anybody know? 2.6? No, it's not. Okay, so look at number 7 here, and let me enlarge that a little bit so that we can see it clearly on the screen. Here it is. Here's a picture. If you carefully read the words, a rectangle has one corner in the quadrant, in the first quadrant of the graph of y equals negative 16 minus x squared, and another point at the origin. And so those are corners of a rectangle. In other words, we're going to be on the graph at some location x, y. Let me try to get my pen here so it's not in the writing. We're going to be at a point x, y on the graph of the quadratic function shown, and the other corner of the rectangle is going to be at the origin. And then they ask us to build some equations associated with that. Build some equations associated with that. So let's go up on the board now and talk about this. Modeling. And so this is a simple example. So we have a function given to us, y equals 16 minus x squared. Now what you should realize from our transform background is this is the equation minus x squared plus 16. What you should be able to see now, based on our past discussion, is that this is an upside down parabola, turned upside down because of the negative. Everybody feel good? And then what are we doing with the 16 here? We're adding 16 to the y values, right? So this is going to then kick it up 16. So we end up with the picture they showed us in the book. But you should be able to do this. If they just gave you this equation, you should be able to sketch this thing. So we have a picture of a parabola up here looking like that. With a vertex up here at 0, 16, and it opens downward. While we're at it, what's the x-intercept, folks? If you wanted to find the 0 here, if you wanted to find this 0, (16 to the right? Let's try it. If you put 16 in here, do you get 0 for y? If you put 16 in for x, do you get 0 for y? 4. Okay. So what you're doing to find that 0 is you're letting y equal 0. Kick the negative x squared to the other side. and you get x equals what? When you undo the squaring process by square rooting, you get plus or minus. Very good. Plus or minus 4, don't you? So you get a 0 over here, and there's also 1 over here. Right? Okay. Now, the modeling that they ask us to do with this problem is they said, we want to lay a rectangle inside the first quadrant. Here's our first quadrant. We want to lay a rectangle in here that touches the graph at location xy, and has one corner there, and the other corner, it says, is at the origin. So if I build a rectangle that has this point as a corner and this point as a corner, then I have to build it looking like that, don't I? What's this x value right here? I answered it already. What is this x value here? X, okay. How tall is this thing right here? Y tall, right? Or isn't it 16 minus x squared tall? Isn't that the height? And isn't this the base? Feel good? So let's see if we can write an equation now, a model that describes the area of that rectangle. The area of that rectangle. You know from your pre-algebra background that a rectangle has area base times height. The area equals base times height, and the base happens to be x, and the height happens to be 16 minus x squared. Feel good? Everybody happy? Okay. And so this is an area formula for the rectangle, is it not? For different values of x. For different values of x. Area of the rectangle. All right. Is there a restriction, folks, on the domain of this model? Is there a restriction on the domain? Has to be positive, because otherwise we wouldn't have a rectangle if we had some negative base, right? So you got to have positive x. Any other restrictions? Has to be bigger than 0. And in the back? 4. Can't be any bigger than 4, can it? So doesn't the area of this rectangle have to be trapped in a domain where x is greater than 0? Here's your domain, and less than 4? Otherwise you wouldn't have a rectangle. Otherwise you would not have a rectangle. If this thing was out here near 4, what if the base was out here near 4? Wouldn't it look something like that? Very flat. And what if the base was very small, like near 0? Wouldn't it look something like this? If I could draw well, right? And as you get close to 0, what's the area turn into? 0. And if the base gets near 4, the area turns back towards 0 again, doesn't it? Okay. What kind of a polynomial is this? See it? You all see it? Isn't this, I'm going to leave a little space for a reason. If I multiply this out, isn't this a negative x cubed plus 16x? If you multiply this x times this binomial, right? Okay, so now what we want to do is we've built a model for the area of the rectangle for variable base length, variable length of the base. And what we want to do is to draw a sketch of this. Can we factor this thing shown here anymore?
That's a difference of squares.
Ah, a square minus b square, we talked about that a while ago. This is a 4 minus x times a 4 plus x, isn't it? Okay, so we could factor this thing some more. And so this is called the factored form. This is the factored form. This is called the general form. Okay. All right? So let's draw a quick picture of this. What would be the zeros of this function? Here's a cubic function, folks. What would be the zeros? X equals what? 0 would turn this into 0, wouldn't it? And if x equals 4, we have a 0, and also over at negative 4. This is a cubic. Isn't it an upside down cubic? Go back to your library. It's an upside down cubic. So instead of doing the usual cubic thing, like my hand's waving, okay, it's upside down, which means it goes up left and comes down right. Looking like this. Up left, down right in its behavior. We're going to study these in more detail later. Now, what portion of the domain is good for this model? What portion of the domain? Here's a picture of the whole thing, but this is not good for the model. Just this. Just that, isn't it? Just that. So just that portion of the domain is physically available to us, and this is really a hole in the graph because of our restricted domain up here. Okay, now here's what's really exciting about this. What choice of x will give us the biggest area rectangle inside here? 4 makes 0. You're guessing that this is a parabola. Is that a parabola? No? Okay. So somewhere between 0 and 4 is the location where you're going to get the maximum area, right? The maximum area. And how much time do I have? About a minute. And we've got our fancy graphing calculator, don't we? So let's jump back to the calculator real quick. And I think I have enough time to do this. Let's get the answer before we finish here. And time is running out. Here we go. And I have to kick this function into here real quickly. So it's going to be x times the quantity 16 minus x squared. I'm going to set a viewing window based on what we just talked about, minus 2 to 5, 1. And then say, oh, how about minus 10 to say 20? That may not be too good. And let's try 5 on that, see what I get. Shoots off the top. I don't like it. What I'm going to do is make my window a little higher. Let's make it 30. Now I'm going to jump to my calculate features to go maximum. Calculate, go to maximum feature, number 4. Lower value, maybe 10. Whoops, sorry. Did something wrong. Calculate, maximum, number 4. Left bound, didn't I say 5, 10, 15? Yeah. 10 I think should work. What's wrong? Excuse me? Let me go back to it. Shouldn't this be 5, 10, 15, 20? Hold it.
Why don't you just arrow over?
Oh, I'm sorry, my scaling was wrong. I had a scale of 1 there, so I had an unreasonable value. So back to this, how much, I'm going to do it. We're going to make it. Here we go. So I'm going to use a 2, and I'm going to use a 3 for my left and right. See the arrows? And I'm going to guess 2.5. And there we go, folks. The maximum area, enclosed area, occurs when the base is 2.309 and the maximum area value is 24.63. So that would be how you optimize to come up with the largest enclosed area underneath that parabola. And I think we're out of time. So that'll do it for today. And your homework quiz, I'm going to let you take until Tuesday at 10 a.m. to do that. And I haven't built it yet. I'm going to do it right now, and it'll be available to you starting at noon.